Hey Bob, I've been going through the June 2026 papers this past week, and there's a lot to unpack. Before I dive into specifics, I'd love to hear your high-level take. What stood out to you as the big themes this month?
Happy to help, Alice. Honestly, two themes jumped out at me. First, there's this surge of AI-assisted quantum code discovery where large language models are actually being used to design quantum error-correcting codes. And second, there's real experimental maturation on both the neutral atom and photonic hardware fronts. We're moving from proof of concept toward things that look genuinely deployable. There's also a strong current of fault tolerance architecture work tying it all together.
Let's start with that LLM code discovery angle since it's so striking. I saw two papers on it. Cruz-Benito and colleagues did an evolutionary workflow for Bivariate bicycle codes, and then there's the structured concept evolution paper by Liu and Marquardt. How do those compare?
Great pairing because they attack the same problem from slightly different philosophies. The Cruz-Benito work, evolutionary discovery of bivariate bicycle codes with LLM-guided search, is very engineering-minded. They have the LLM mutate actual Python programs that generate code candidates, then run them through a rigorous validation pipeline with rank checks, distance certification, and equivalence to duplication. What I love is the honesty about cost, roughly 140 hours and $400 in inference, and they recover known good codes plus new finite length ones, like an indecomposable 208 qubit code. It's grounded and reproducible.
And the Liu-Marquardt approach is more abstract?
Exactly. Structured concept evolution is cleverer about what the LLM manipulates. Instead of asking it to design codes from scratch or just mutate raw programs, they evolve structured concepts, algebraic specifications paired with executable code that realizes them. The mutations are hierarchical, touching the group algebra, the protograph geometry, or the base space. The payoff is that they reach beyond standard abelian constructions into non-abelian group families, which is territory that bivariate bicycle codes don't cover. So Cruz-Benito optimizes a known family deeply, while Liu-Marquardt broadens the search space itself.
That's a nice distinction, depth versus breadth. Is there a risk here that the LLM is just doing fancy interpolation and the real credit belongs to the validation pipeline?
That's the right skeptical question. In the Cruz-Benito paper, the validation pipeline absolutely does the heavy lifting on certification. The LLM is more of a proposal engine. And they're candid that the LLM guides mutations rather than reasoning about codes. Liu-Marquardt push a bit harder on the claim that the structured grammar lets the LLM contribute meaningful structure, but even there, the rigorous BP plus OSD evaluation is what tells you a candidate is actually good. So I'd say these are best viewed as guided search accelerators, not autonomous discoverers. Still, that's genuinely useful when the design space is combinatorially huge.
Sticking with qLDPC codes, there's also the Barbell codes paper by Choi and colleagues. That one seems more hardware-focused. How does it fit in?
Yes, Barbell codes, qLDPC codes for superconducting quantum hardware tackles the practical elephant in the room. qLDPC codes are wonderful on paper because of their low overhead, but they demand non-local connectivity that fixed layout superconducting chips hate. The Barbell construction is designed so that all the required 2-qubit interactions map onto a realistic chip layout, and critically, the hardware complexity stays constant as you increase code distance. They report preserving information at a physical error rate of 10 to the minus 4 for trillions of cycles with under 30 data qubits per logical qubit. That's the kind of concrete co-design that makes qLDPC feel real for superconducting platforms.
So together, the LLM papers are exploring the code space while Barbell is asking whether we can even build these things. That's a healthy division of labor. Speaking of building, there were several experimental hardware demonstrations. The atom computing Toric code paper caught my eye.
That one is a milestone. Quantum error correction with the Toric code from atom computing demonstrates repeated syndrome extraction, up to 90 cycles, with mid-circuit measurement and, crucially, replacement of lost atoms, including reloading a qubit reservoir. Atom loss has been the Achilles heel of neutral atom systems for sustained error correction, so showing you can reload and keep going indefinitely is a big deal. And they see the larger distance code achieving a lower absolute logical error rate, which is the scaling signature you want. It's the first neutral atom demonstration of QEC that's genuinely scalable to arbitrary depth.
The reservoir reloading is such an elegant solution to a stubborn problem. On the photonic side, there's the big quantum dot paper from Senelart's group and the FPGA feed-forward paper. Are those part of the same story?
They're complementary pieces of the photonic quantum computing puzzle. Industry-ready spin-photon interfaces is the headline result. Thousands of quantum dot devices from a 3V pilot production line, which is a manufacturing story as much as a physics one. They demonstrate near-unity photon purity stable over tens of minutes, record Wigner function negativity, 7-partite spin photon entanglement, and photons from distant sources being as indistinguishable as those from a single source. That last point is essential for networked architectures. The word foundry compatible is the real news, reproducibility at scale.
And the FPGA paper handles the control side?
Right. FPGA-based feed-forward system for photonic quantum computing addresses a very practical bottleneck for continuous variable measurement-based schemes, which need fast adaptive measurements and displacements via feed-forward. A lot of prior work faked this in post-processing, which doesn't scale. Duggan and colleagues built a real-time system with a high-efficiency homodyne detector over 95% quantum efficiency and total latency under 200 nanoseconds. It's unglamorous, but exactly the kind of engineering that turns theoretical CV protocols into runnable ones. So you've got sources, and now you've got the real-time control glue.
That makes me think about decoders too, since real-time control needs fast decoding. The foundation decoder paper by Juan and colleagues seemed to address a scaling problem. What's the innovation there?
Efficient foundation decoders for fault-tolerant quantum computing tackles a real pain point with neural decoders. Training cost explodes at large code distances. Their neural transfer unification idea exploits the algebraic structure shared across a code family, so knowledge learned on a small code accelerates training on larger ones. It's essentially transfer learning tailored to code scaling. They show their transformer decoder beating correlation-aware matching on distance 19 and distance 25 surface codes, and beating relay BP on a Bivariate bicycle code in the low-error regime. The cross-distance amortization is the clever bit. It makes high-capacity neural decoders more economically viable.
Is that a common thread that decoding and error correction are increasingly leaning on machine learning?
Very much so. Between the neural foundation decoders and the LLM-guided code discovery, machine learning is threading through the whole error correction stack now, from designing codes to decoding them. It reflects a maturity shift. The problems have become search and optimization problems at scales where human intuition plateaus and ML tools fit naturally. The caveat is always verification. You need the rigorous certification layer underneath, so you're not trusting a black box on something as critical as fault tolerance.
That's a good reminder. On the more theoretical side, there were some ambitious unification papers. Wang's all about quantum error correction, claims distillation, mitigation, and dynamical decoupling are all special cases of one framework. Is that a genuinely useful lens or more of a conceptual tidy-up?
A bit of both, and I mean that positively. Wang extends error correction to state adaptive and channel adaptive settings and multi-stage coding, and under that umbrella, these techniques we usually teach as distinct suddenly appear as points on a spectrum. Conceptually, that's satisfying and pedagogically valuable. Whether it changes practice depends on whether the unified view suggests new constructions, and Wang does propose a self-correcting memory model as a downstream fruit. I'd file it as a framework paper whose real payoff will be judged by what it enables next.
There was another space-time flavored framework, the space-time lifting paper by Xu, Wang, and Liu. That sounded more construction-oriented.
Yes, and it's a nice example of fault tolerance being treated as an inherently space-time problem rather than a static code problem. A framework for low-overhead quantum fault tolerance via space-time lifting uses fault complexes, a homological way of viewing an entire protocol over time as a single object. Their space-time lifting builds these complexes from symmetry-reduced product structures, and they achieve almost linear fault distance in the total space-time cost, which meaningfully beats existing foliation-based constructions. They also connect it to measurement-based cluster state protocols and fault-tolerant teleportation. So unlike Wang's conceptual unification, this one directly yields better scaling protocols.
Continuing the architecture theme, Wang and colleagues proposed a 3-layer fault-tolerant architecture, and there's a reference-style handbook of error-correcting codes. Those feel like consolidation efforts for the field.
They are, and consolidation is a sign of a maturing field. A 3-layer architecture for fault-tolerant quantum computing borrows from classical computer architecture to define a hardware-agnostic stack, with special attention to the intermediate fault tolerance layer that bridges logical programs and physical execution. It's about standardizing interfaces so modular, heterogeneous systems can be organized coherently. The Handbook of Error-Correcting Codes by Albert and Feist is the print incarnation of the Error Correction Zoo, a curated map of codes and their relationships to lattices, designs, groups, and phases of matter. Both are the kind of infrastructure that lets newcomers, like you, orient in a sprawling landscape.
I'll definitely be leaning on that handbook. There was also a distributed computing thread. Core and colleagues studied network constraints on fault-tolerant distributed quantum computing, and there was a satellite scheduling paper doing distributed quantum computing too. How mature is distributed QC right now?
Still early, but the June work sharpens what actually matters. Impact of network constraints on fault-tolerant distributed quantum computing by Core and colleagues is valuable because it jointly models surface code operations QPU connectivity, and realistic network limits like finite entanglement generation rates and bandwidth contention. The key finding is that optimal code distance and resource allocation shift depending on network characteristics, trade-offs that are invisible if you model computation and communication separately. That's an important corrective because a lot of distributed QC analysis treats the network as an idealized afterthought.
And the satellite scheduling paper by Braidwood and colleagues actually applied distributed quantum methods to a real problem, wildfire tracking, right?
That's partitioned iterative quantum scheduling of satellites. And it's honest about where we are. They apply an iterative quantum algorithm framework with analytic guarantees plus a distributed parallelization scheme to real wildfire datasets. The candid conclusion is that their quantum subprocesses are still too small to show quantum advantage, but they're validating the techniques and building the plumbing for utility-scale distributed problems. I appreciate papers that resist overclaiming. They're forging the path rather than declaring victory.
That honesty extends to the neutral atom optimization paper too, doesn't it? Tarquini and colleagues did emergency hub placement on Pascal's Fresnel processor.
Yes, emergency hub placement with a neutral atom quantum computer is a nice companion to the satellite work, another real-world graph optimization frame for disaster response. They formulate emergency center placement as a minimum dominating set problem and use the neutral atom device as an independent set sampler, then refine classically. They actually solved instances up to 100 nodes on real hardware, and despite noise, the quantum-generated samples enabled near-optimal solutions. The takeaway is that analog neutral atom machines can already be useful engines inside hybrid classical pipelines for structured graph problems.
That hybrid framing appears a lot. There's also Aparicio Morales and colleagues on architecting hybrid quantum classical software systems, which sounds like software engineering rather than physics. Is that a growing niche?
It is, and it's a healthy sign the field is thinking about deployment. Architecting hybrid quantum classical software systems applies service-oriented architecture principles to the messy reality that quantum algorithms only cover a narrow slice of real applications and need specialized hardware. They formalize an architectural style and provide a method to explore the design trade-off space with quantitative guarantees, so you can dynamically pick the best hybrid or purely classical configuration based on quality of service criteria. It's the kind of systems engineering thinking that becomes essential once quantum is a component in a larger stack rather than a standalone demo.
Let's touch on the variational and machine learning theory papers. Since there were several, Mandel and colleagues argue for a separation between statistical complexity and trainability. And there's the entanglement scaling paper by Arapantonis and colleagues. What did you make of those?
Both push back on tidy intuitions. Separation of statistical complexity and trainability challenges the folk belief that more expressivity, meaning random state-like behavior, inevitably kills trainability via barren plateaus. Mandel and colleagues show that statistical signatures of randomness can appear well before trainability degrades, using structured circuits on clusterizing and Toric code like Hamiltonians. Their explanation is about locality, spectral correlations develop at shallow depth while global randomization hasn't kicked in. The lesson is that the usual diagnostics of complexity don't by themselves predict whether you can train a circuit.
And the entanglement scaling one?
Entanglement scaling and problem structure in QAOA makes an interesting methodological point that suboptimal parameter training can distort the entanglement profile you observe, obscuring its true scaling. With a strong optimizer, they find QAOA on max-cut exhibits entanglement scaling consistent with fermionic Gaussian states up to a factor, whereas adiabatic computation shows schedule-dependent profiles that scale differently. So entanglement structure can actually distinguish these two paradigms. Together with the Mandel paper, there's a shared cautionary message. If your optimizer is weak, you'll draw wrong conclusions about the fundamental properties of your algorithm.
That's a subtle but important point about not conflating optimization artifacts with physics. There were two more QML-flavored works, the Anyone's paper by Zhang and colleagues and Monbrosso's thesis. Anything noteworthy?
The Anyone's paper is genuinely novel in its angle. Enhancing quantum machine learning with Anyone's asks whether particle exchange statistics, an underexplored quantum resource, can help learning. They build a kernel framework spanning bosonic, fermionic, and anyonic statistics, and find that fractional exchange phases access feature space directions the symmetric or anti-symmetric limits can't. With anyonic kernels outperforming on benchmarks, it's a fresh conceptual ingredient for QML. Monbrosso's thesis, quantum machine learning for industrial applications, is more of a synthesis with solid results on barren plateau-free Hamming weight-preserving circuits and subspace-preserving algorithms with provable separations. Both reinforce that structured circuits, not generic ones, are where the promise lies.
Now, there were a few papers on the cryptographic and security implications side, which feels like a different corner of the field. The post-quantum readiness measurement and the Bitcoin Ethereum threat assessment. Are those worth attention for someone focused on computing?
Absolutely, because they ground the why does this matter question. Measurement study of post-quantum readiness of Internet 2026 surveys over 32,000 domains and finds sobering gaps. About half still use classical key exchange and 0% have adopted hybrid post-quantum certificates, leaving authentication exposed to future forgery. The Gerstein-Albert paper, Quantum Horizon, is refreshingly measured about Bitcoin and Ethereum. It separates Shore's threat to signatures from the overhyped Grover threat to mining and produces a bimodal forecast for a cryptographically relevant machine, roughly 1 in 6 by 2035. Their punchline is that timely migration beats even an optimistic machine, so the bottleneck is governance, not physics.
That governance versus technology framing is a useful antidote to alarmism. And there was a QKD thesis on satellite protocols and a security paper on blind quantum computing too. Do those round out the picture?
They do, on the defensive side. The satellite QKD thesis by Muskan carefully evaluates BB84, B92, BBM92, and E91 under realistic atmospheric conditions and finds high-dimensional BB84 gives better key rates and noise tolerance, useful practical guidance for LEO links. On the delegation side, Van Dam and colleagues' Optimizing Resource Costs paper for verifiable blind quantum computing is quietly important. It turns the notoriously fiddly parameter tuning of a noise-robust VBQC protocol into a formal optimization problem, so you can actually compute the minimal number of rounds for a target security level and hardware noise. That's the kind of thing that makes secure delegation practically deployable rather than just provably possible.
There are a couple I haven't asked about, the transmuon characterization tutorial and Abramski's higher order quantum computation paper. They seem to sit at opposite ends of the abstraction spectrum.
They really do, and I like that both exist in the same month. A tutorial for characterizing transmon qubits by Souza and colleagues is pure hands-on know-how, walking through the entire experimental workflow from cryogenic wiring to pulse calibration and readout optimization on a commercial 5-qubit chip. It's the kind of tacit knowledge document that's usually locked in lab notebooks, so publishing it lowers the barrier for new experimentalists. Abramski and Jagadisan's essential unitarity for higher-order quantum computation is at the categorical semantics end, generalizing unitarity to higher-order interfaces and characterizing objects like the coherent quantum switch. It's foundational theory for reasoning about quantum programs that take other quantum programs as inputs.
It's remarkable how wide the spectrum is, from wiring up a fridge to compact closed categories, all in 1 month. If you had to name the single most consequential development of June 2026, what would it be?
If I'm forced to pick one, I'd say the atom computing Toric code demonstration, because sustained arbitrary depth error correction with qubit reloading removes a fundamental doubt about whether neutral atoms can do long computations. But I'd give an honorable mention to the industry-ready quantum dot sources, since foundry scale reproducibility is the unglamorous prerequisite for photonic scaling. The theory and LLM discovery work is exciting, but this month the experimental hardware told the most convincing story about crossing thresholds.
That's a satisfying way to frame it. The hardware is finally catching up to the theory's ambitions. This has been incredibly clarifying, Bob. My big takeaways are the ML-assisted error correction stack, the experimental maturation on neutral atoms and photonics, the growing seriousness about distributed and hybrid systems, and the sober security migration timelines. Thanks for walking me through all of it. I've got a much clearer map of where the field is heading now.
My pleasure, Alice. You've picked out exactly the right connective threads. If there's one meta lesson from June, it's that quantum computing is transitioning from isolated breakthroughs to integrated engineering, codes talking to decoders, sources talking to control systems, and quantum modules talking to classical networks. Keep asking these cross-cutting questions. That's where the real understanding lives. Let's do this again next month.